Welcome students to the second lecture on the operational amplifier. I am Dr. Kirti Vyas from Arya College of Engineering IT. So let's get started with the lecture. As you all know, the operational amplifier is a direct coupled high gain amplifier which consists of one or more differential amplifiers, and it is followed by a level transistor and an output stage. This we have already discussed in our earlier lecture, that how a differential amplifier works, and through this particular block diagram of op-amp which is given in the slide, you can see the op-amp is made up of several stages. It is a cascade of input stage, which is basically dual input balanced output differential amplifier, which we have already discussed in our earlier lecture. Next one is known as an intermediate stage. This one is a dual input unbalanced output type of a differential amplifier, and since, as you can see, in both of the input stage and intermediate stage the DC coupled amplifier are being used, so obviously there has to be some level shifting at the emitter region. That particular level shifting has been adjusted by the third block, which is known as a level shifting circuit. Last one is an output stage. Basically, this particular output state is a push-pull complementary amplifier, and it increases the output voltage swing and rises the current supplying capability of the op-amp. One of the feature which is provided by this particular last stage is low output resistance. This is some more insight into the level translator, or you can say a level transistor type of circuit. As I already told you that because of the direct coupling, the DC level at the emitter rises from stage to stage. So there is a particular resistance R1 and R2 applied at the emitter terminal, which are used to balance the shift in the DC voltage and bring that to the initial zero level. Now, this particular figure 3 shows the complete op-amp circuit having input differential amplifier with balanced output. This you can see by having a look at the input stage, which has been given by dashed green line, and second is the intermediate stage, which consists of unbalanced output. Next one, as you can say, is a level shifter transistor, and the last one is a push-pull configuration. So you can see a differential amplifier is basically a cascade of op-amp is a cascade of many differential amplifiers, a level shifter, and at the output we are having a push-pull configuration. Now, in order to have the insight into this particular differential amplifier, let's analyze a particular cascaded differential amplifier, which is shown as figure 1. And for this particular figure, you can see what are the value of the basic resistors. These are labeled, and the HFE value which has to be assumed is 100, with the base emitter potential drop equals to 0.715 volt. What we have to find out in this circuit is the collector current and collector to emitter voltage for each of the transistor, the overall voltage gain, the input resistance, and the output resistance. Now, for the solution, we need to determine the collector current and a collector to emitter voltage of both of the transistor Q1 and Q2. Once again, look at the slide. Q1 and Q2 are the first transistors at the very input of this particular cascaded differential amplifier, and assume that the inverting and non-inverting inputs are grounded. Here we also assume that the collector current is equal to the emitter current in Q1 and Q2, and we obtain the emitter current from the Q1 transistor from the already derived equation discussed in earlier lecture. This gives the value of IC1 and IC2. Now we calculate the voltage between collector and emitter for Q1 and Q2 using collector's current. It is given by our equation Vc1, and thus we find out the value of Vc1 and Vc2. Same, we are having the value of VCE1 equals to VCE2 equals to VC1 minus VE1, which is equals to 8.545 volt. Next, we determine the collector current in Q3 and Q4. By applying the KVLs, we find out the value of IE3 and VC3, and therefore we are able to find VCE3, which is given as 2.2 volt. So for Q1 and Q2 we have derived the value of VCQ and VCEQ, where Q stands for the quiescent point, and for Q3 and Q4 the value derived are ICQ is equals to 0.569 milliampere and VCEQ equals to 2.2 volt. For the P part, we have to calculate the AC emitter resistance RE of each stage and then its voltage gain. So RE, according to the equation, is equals to Vt, where Vt stands for volt equivalent of temperature, which is 25 millivolt upon IE1. Substituting the value of IE1, we find out the value of RE1 dash, which is equals to RE2 dash, and RE3 dash, which is equals to RE4 dash. Finally, for the voltage gain, we have V output of first stage upon the input difference of input applied, which is also equals to RC1 in parallel to RI2 upon RE1. Substituting the value, we have the differential amplifier gain equals to 80.78. Here the value of RI2 has already discussed in earlier lectures, come out to be twice beta AC RE3 plus R dash E. The second stage is dual input unbalanced output differential amplifier with swamping resistor RE dash. The voltage gain of this one will be V output upon V output 1, which is equals to 4.17, and the overall voltage gain of the cascade is equals to gain of the first stage into gain of the second stage, and hence the product give us 336.85. Now last, we have to find out the input resistance of the cascaded differential amplifier. It is the same as the input resistance of the first stage, which is Ri is equals to twice beta AC into Re1, which is 5.06 kilo ohm. Also, we have to find out the output resistance of the cascaded differential amplifier, which is same as the output resistance of the last stage, and hence RO is equals to RC equals to 1.2 kilo ohm. So this was basically our analysis for cascaded differential amplifiers which are used to make a op-amp. The symbolic diagram of op-amp is given in this particular figure. Here we can say the input terminals are inverting input and a non-inverting input. The op-amp is applied by plus VCC and minus VCC at the pin number 7 and 4 respectively, and from the 6th we take the output. 741 is most commonly used op-amp available in the IC package. This is a 8-pin DIP chip. Now we discuss parameters of op-amp. One of the important parameter of op-amp is input offset voltage. Since this particular fact is already discussed in our earlier classes, that the transistors which are used to make the op-amp should be identical enough. Since the transistors are identical enough, if we give the same input to both of the inverting and non-inverting terminal, the output should be 0. If it is not so, we can say the transistors were not identical and not perfectly matched. So, what about the input offset voltage? Why to read about it? The input offset voltage is defined as a voltage that must be applied between the two input terminals of an op-amp to null or zero the output. This will be a case when the transistor used for the op-amp configuration are not matched. Our figure 2 shows two DC voltages that are applied to input terminals to make the output 0. That is, the input offset voltage is denoted by V stands for voltage, I stands for input, O stands for offset voltage. That is why it is named as VIO is equals to VDC1 minus VDC2. For 74C op-amp, the maximum value of input offset voltage is 6 millivolt. It means that a voltage of plus minus 6 millivolt is required to one of the input to reduce the output offset voltage to 0, or you can say perfectly match the transistor workings. In our next lecture, we will discuss some more parameters of op-amp so that we can be able to design certain circuits out of this op-amp. Thank you.